So today I wanted to then, the title of today's lecture is, what is it? The Universal Principle of Risk Management, Pooling and the Hedging of Risk. And what I'm really referring to is, I think, the very original, the deep concept that underlies theoretical finance. I wanted to get that first. And it really is probability theory and the idea of spreading risks through risk pooling. So this idea is it's an intellectual construct that appeared at a certain point in history, and it has had amazing number of applications, and finance is one of these. So I wanted, some of you, this incidentally will be a more technical of my lectures, and so it's a little bit unfortunate that it comes early in the semester. For those of you who've had a course in probability and statistics, there will be nothing new here. Well, nothing in terms of the probability theory new. Others, though, I want to tell you that it doesn't, if you're shopping, I had a student come by yesterday and ask that he's a little rusty in his math skills, and should he take this course? And I said, well, if you can understand tomorrow's lecture, it's today's lecture, then you should have no problem. So I wanted to start with the concept of probability. And you know what a probability is? It's we attach a probability to an event, okay? So what is the probability that the stock market will go up this year, okay? I would say my personal probability, 0.45, and so that's because I'm a bear, but you know what that means, that 45 times out of 100, the stock market will go up, and the other 55 times out of 100, it will stay the same or go down. That's a probability. And now, you're familiar with that concept, right? If someone says the probability is 0.55 or 0.45, well, you know what that means. But I wanted to emphasize that it hasn't always been that way, and that probability is really a concept that arose in the 1600s. Before that, nobody ever said that. Ian Hacking, who wrote a history of probability theory, searched through world literature for any reference to a probability and could find none anywhere before 1600. So there was an intellectual leap that occurred in the 17th century, and it became very fashionable to talk in the terms of probabilities. It spread throughout the world, the idea of quoting probabilities. But it's funny that such a simple idea hadn't been used before. Hacking points out that the word probability and probable was already in the English language. In fact, Shakespeare used it. But what do you think it meant? He gives an example of a young woman who is describing a man that she likes. And she says, I like him very much. I find him very probable. Okay, what do you think she means? Can someone answer that? Does anyone know Elizabethan English well enough to tell me? What is a probable young man? Anyway, I'm asking for an answer. See, it sounds like people have no idea, right? Anyone venture a guess? No one wants to venture a guess.
He can father children.
That he can father children. I don't think that's what she meant. But maybe. No, what apparently she meant is trustworthy. Okay? That's a very important quality in a person, I suppose, right? So if something is probable, you mean that you can trust it. Okay? And so probability means trustworthiness. And so You can see how they moved from that definition of probability to the current definition. But Ian Hacking, being a good historian, thought, someone must have had some concept of probability going before, even if they didn't quote it as a number. They must have been in their head or in their idea. So he searched through world literature to try to find some use of the term that preceded the 1600s. And he concluded that there were probably a number of people who had the idea, but they didn't publish it, and it never became part of the established literature. Partly because, he said, throughout human history, there has been a love of gambling. And probability theory is extremely useful if you are a gambler. And Hacking believes that there were many gambling theorists who invented probability theory at various times in history and never wrote it down and kept it as a secret. And he gives an example. I like to, he gives an example from a book that, or it's a collection. You know this? I think there's, this is a collection of epic poems written in Sanskrit, and that goes back, it actually written over a course of 1,000 years, and it was completed in the 4th century. Well, there's a long story in the Mahabharata about an emperor called Nala, and he had a wife named Damayanti, and he was a very pure and very good person. But there was an evil demon called Kali who hated Nala and wanted to bring his downfall. So he had to find a weakness of Nala. And he found finally even though Nala was so pure and so perfect, he found one weakness, and that was gambling. Nala couldn't resist the opportunity to gamble. So the evil demon seduced him into gambling aggressively. And you know how sometimes when you're losing, you redouble and you keep hoping to win back what you've lost? In a fit of gambling, Nala finally gambled his entire kingdom and lost. Okay, it's a terrible story. And Nala then had to leave the kingdom and his wife. And they wandered for years. He separated from her because of dire necessity. They were wandering in the forests, and he was in despair, having lost everything. But then he meets someone by the name of, who do we have here? We have Nala, and he meets this man, Rituparna. And this is where probability theory apparently comes in. Rituparna tells Nala that he knows the science of gambling, and he will teach it to Nala. But it has to be done by whispering it in his ear, because it's a deep and extreme secret. And Nala is skeptical. How does Rituparna know how to gamble? And so Rituparna tries to prove to him his abilities, and he says, see that tree there? I can estimate how many leaves there are on that tree by counting leaves on one branch. So Rituparna looked at one branch and then estimated the number of leaves on the tree. And Nala was skeptical. So he stayed up all night and counted every leaf on the tree. And it came very close to what Rituparna said. And so he next morning believed Rituparna. Now, this is interesting, Hacking says, because it shows that sampling theory was part of Nala's theory. You don't have to count all the leaves on the tree. You take a sample, and you count that, and then you multiply. So anyway, the story ends. Nala goes back, and now armed with probability theory, we assume, he goes back and gambles again. He has nothing left to wager except his wife. So he puts her and gambles her. But remember, now he knows what he's doing. And so he really wasn't gambling his wife. He's really a very pure and honorable man. But And so he won back the entire kingdom, and that's the ending. So anyway, that shows that I think probability theory does have a long history. But it not being an intellectual discipline, it didn't really inform a generation of finance theory. When you don't have a theory, then you don't have a way to be rigorous. So it was in the 1600s that probability theory started to get written down as a theory. And many things then happened in that century, which I think are precursors both to finance and to insurance. One was, in the 1600s, people started constructing life tables. What is a life table? It's a table showing the probability of dying at each age, for each age and sex. Okay? That's what you need to know if you're going to do life insurance. So they started to do collecting of data on mortality, and they developed something called actuarial science, which is estimating the probability of people living. And so that then became the basis for insurance. Now, actually, insurance goes back to ancient Rome in some form. In ancient Rome, they had something called burial insurance. You could buy a policy that protected you against your family not having the money to bury you if you died. And in ancient culture, people worried a great deal about being properly buried. So that's an interesting concept. They were selling that in ancient Rome. But you might think, well, why just for burial? Why don't you make it into a full-blown life insurance? And you kind of wonder why they didn't. I think it's maybe because they didn't have the concepts down. In Renaissance Italy, they started writing insurance policies. But I read one of the insurance policies. It's in the Journal of Risk and Insurance. They translate a Renaissance insurance policy. And it's very hard to understand what this policy was saying. I guess they didn't have our language. They didn't. They were intuitively halfway there, but they couldn't express it. So I think the industry didn't get really started. So I think it's the invention of probability theory that really starts it. And that's why I think theory is very important in finance. And some people date fire insurance with the fire of London in 1666. The whole city burned down practically in a terrible fire. And fire insurance started to proliferate right after that in London. But you kind of wonder if that's a good example for fire insurance, because if the whole city burns down, insurance companies would go bankrupt anyway, right? London insurance companies would, because the whole concept of insurance is pooling of independent probabilities. And so, but nonetheless, that was the beginning. We're also going to recognize, however, that insurance got a slow start because, and I believe it is because people could not understand the concept of probability. They didn't have the concept firmly in mind. There's a lot of aspects to it. There's in order to understand probability, you have to take things as coming from a random event. And people don't clearly have that in their mind from an intuitive standpoint. They have maybe a sense that I can influence events by willing or wishing. And if I think that, if I have kind of a mystical side to me, then probabilities don't have a clear meaning. And it's been shown that even today, people seem to think that, that they don't really take, at an intuitive level, probabilities as objective. So for example, if you ask people how much they would be willing to bet on a coin toss, they will typically bet more if they can toss the coin. Or they will bet more if the coin hasn't been tossed yet, and it could have been already tossed and concealed. Why would that be? It might be there's just some intuitive sense that I can, I don't know, I have some magical forces in me and I can change things. So the idea of probability theory is that, no, you can't change things. There are these objective laws of probability out there that guide everything. Most languages around the world have a different word for luck and risk, or luck and fortune. Luck seems to mean something about you. I'm a lucky person. I don't know what that means, like the god or gods favor me, and so I'm lucky. This is my lucky day. Probability theory is really a movement away from that. And so we then have a mathematical, rigorous discipline. So now I'm going to go through some of the terms of probability here, and this will be review for many of you, but it'll be something that we're going to use in the. So I'll use the symbol p, or I can sometimes write it out as probability to represent a probability. Okay, and it is always a number that lies between 0 and 1, or between 0% and 100%. Okay, percent means divided by 100 in Latin, right? So 100% is 1. Okay, and so this is the probability. If the probability is 0, that means the event can't happen. If the probability is 1, it means it's certain to happen. If the probability is, does everyone see this from over there? I don't know if I can move. I can't probably move this, or can I? Yes, I can. Now, can you now? You're the most disadvantaged person, and you can see it, right? That's the basic idea. Now, one of the first principles of probability is the idea of independence. Okay. So the idea is that probability is the measures the likelihood of some outcome. Let's say the outcome of an experiment. Okay, like tossing a coin. You might say the probability that you toss a coin that it comes up heads is a half. Okay, because equally likely heads and tails. Independent experiments are experiments that occur without relation to each other. So if you toss a coin twice and the first experiment doesn't influence the second, we say they're independent. And so there's no relation between the two. And one of the first principles of probability theory is called the multiplication rule. And that says if you have independent probabilities, the probability of two events is equal to the product of their probabilities. So the probability of A and B is equal to the probability of A times the probability of B. Okay? That wouldn't hold if they're not independent. The theory of insurance is that ideally an insurance company wants to insure independent events. Okay? And so ideally life insurance is insuring people, or fire insurance is insuring people against independent events. So it's not the fire of London. It's the problem that sometimes people knock over an oil lamp in their home and they burn their own house down. And so it's not going to burn any other houses down. It's just completely independent of anything else. So the probability that the whole city burns down is infinitesimally small, right? This will generalize to probability of A and B and C is the probability of A times the probability of B and times the probability of C, and so on. So if their probability is 1 in 1,000 that a house burns down, and there's 1,000 houses, the probability that they all burn down is 1/1000th to the 1,000th power, which is virtually 0. And so insurance companies then, basically, if they write a lot of policies, they have virtually no risk. And so that is the fundamental idea, which may seem simple and obvious to you, but it certainly wasn't back when the idea first came up. One of the incidentally, we have a problem set which I want you to start today, and it will be due not in a week this time because we have Martin Luther King Day coming up, but it will be due the Monday following that. If you follow through from the independent theory, there's a one of the basic relations in probability theory is called the binomial distribution. And I'm not going to spend a whole lot of time on this. But it gives the probability of X successes in N trials. Or in the case of insurance, X, if you're insuring against an accident, the probability that you'll get X accidents in N trials. So the binomial distribution gives the probability as a function of X, and it's given by the formula where P is the probability of the accident. P to the X times 1 minus P to the N minus X times N factorial all over N minus X factorial. And so that is the formula that insurance companies use when they have independent probabilities to estimate the likelihood of having a certain number of accidents. They're concerned with having too many accidents, which might exhaust their reserves. So an insurance company has reserves, and they have enough reserves to cover them for a certain number of accidents, and they use the binomial distribution to calculate the probability of getting any specific number of accidents. So that is the multiplication, the binomial distribution. So I'm not going to expand on this because I can't get into detail. This is not a course in probability theory, but I'm hopeful that you can see the formula and you could apply it. All right? Any questions? Is this clear enough? Can you read my handwriting? Okay, so another important concept in probability theory that we will use a lot is expected value. And so the mean or average, those are all roughly interchangeable concepts. So we have expected value, mean or average. Okay? But we can define it in a couple of different ways depending on whether we're talking about sample mean or population mean. The basic definition, the expected value of some random variable x. I guess I should have said a random variable is a quantity that takes on value. X, if you have an experiment and the outcome of the experiment is a number, then a random variable is that number which comes from the experiment. So for example, the experiment could be tossing a coin, and I will call the outcome heads the number 1, and I'll call the outcome tails the number 0. So I've just defined a random variable. You have discrete random variables like the one I just defined, or there are also which take on only a finite number of values, and we have continuous random variables that can take on any number of values along a continuum. Another experiment would be to say mix two chemicals together and put a thermometer in and measure the temperature. That's another invention of the 1600s, by the way, the thermometer. And they learned that concept in the perfectly natural to us, temperature, right? But it was a new idea in the 1600s. So anyway, that's continuous, right? When you mix two chemicals together, it could be any number. There's an infinite number of possible numbers, and that would be continuous. For discrete random variables, we can define the expected value or mu sub x, that's the Greek letter mu, is the summation I equals 1 to infinity of the probability that x equals x sub I times x sub I. All right? So I have it down that there might be an infinite number of possible values for the random variable x. In the case of the coin toss, there are only 2, but I'm saying in general there could be an infinite number, but they're countable. And so we can list all possible values when they're discrete and form a probability-weighted average of the outcomes. And that's called the expected value. And people also call that the mean or the average often. But you note that this is based on theory. These are probabilities. Okay? In order to compute using this formula, you have to know the true probabilities. There's another formula which applies for continuous random variables, and it's the same idea, except that I'll also call it mu sub x, except that it's an integral. So we have the integral from minus infinity to plus infinity of f of x times x dx. Okay? And that's really, you see, it's the same thing because an integral is analogous to a summation. Those are the two population definitions. F of x is the continuous probability distribution for x. It gives, so that's different. When you have continuous values, you don't have the probability that x equals x sub I because it's always 0. The probability that the temperature is exactly 100 degrees is 0 because it could be 100.00001 degrees or something else, and there's an infinite number of possibilities. So we have instead what's called a probability density when we have continuous random variables. You're not going to need to know a lot about this for this course, but I wanted to get the basic ideas down. So these are called population measures because they refer to the whole population of possible outcomes, and they measure the probabilities. So it's the truth. But there are also sample means. When you get, this is Rituparna, counting the leaves on a tree. You can estimate from a sample the population expected values. And so the population mean is often written x bar. If you have a sample with n observations, it's the summation I equals 1 to n x sub I divided by n. All right? That's the average. You know that formula, right? You count n leaves you count the number of leaves. You have n branches on the tree. You count the number of leaves and sum them up. One would be, I guess I'm having a little trouble putting this into the Rituparna story, but you see the idea. You know the average, I assume. That's the most elementary concept. And so you could use this to estimate either a discrete or continuous expected value. Now, in finance, there's often reference to another kind of average, which I want to refer you to, and which in the Jeremy Siegel book, there's a lot is made of this. And the other kind of average is called a geometric average. And so we'll call that, I'll only show the sample version of it. G of x equals, there's left parentheses, the product I equals 1 to n x sub I to the 1 over n power. All right, can you see that back there? Maybe you have trouble seeing that, but it's different. Instead of summing them and dividing by n, I multiply them all together and take the nth root of them. So this is called the geometric average, and it's used only for positive numbers. So if you have any negative numbers, you'd have a problem, right? If you had one negative number in it, then the product would be a negative number. And if you took a root of that, you might get an imaginary number. So we don't want to use it in that case. But there's an appendix to one of the chapters in Jeremy Siegel's book where he says that one of the most important applications of this theory is to measure how successful an investor is. Okay? So if suppose someone is managing money, have they done well? If so, you would say, well, they've been investing money over a number of different years. Let's take the average over all the different years. Okay? So suppose someone has been investing money for n years, and x sub I is the return on the investment in a given year. What is their average performance? Well, the natural thing to do would be to average them up, right? But Jeremy says that maybe that's not a very good thing to do. What he says you should do instead is take the geometric average of gross returns. Okay. Now, what is the return on an investment is how much you made from the investment as a percent of the money invested. Okay. The gross return is the return plus 1. All right. The worst you can ever do investing is to lose all of your investment, lose 100%. So if we add 1 to the return, you've got a number that's never negative, and we can then use geometric returns. Okay? And so Jeremy Siegel says, really, in finance, we should be using geometric and not arithmetic. And why is that? Well, I'll tell you in very simple terms, I think. Suppose someone is investing your money, and he announces, I have had very good returns. I have invested, and I've produced 20% a year for 9 out of the last 10 years. And so you think, gee, that's great. Well, what about the last year? And the guy says, oh, I lost 100% in that year. Okay. So you might say, all right, that's good. So I would add up 20% a year for 9 years, and then put in a 0, 120, because it's gross return for 9 years, and put in a 0 for 1 year. And maybe that doesn't look bad, right? But you think about it. If you were investing your money with someone like that, what did you end up with? You ended up with nothing. If they have 1 year when they lose everything, doesn't matter how much they made in the other years. So what Jeremy says in the text is that the geometric return is always lower than the arithmetic return, unless all the numbers are the same. And so it's a less optimistic version. And so we should use that. But people in finance resist using that because it's a lower number. And when you're advertising your return, you want to make it look as big as possible. Okay. We also need some measure of, we've been talking here about measures of central tendency only. And in finance, we need as well measures of dispersion. That's how much something varies. Central tendency is a measure of the center of a probability distribution of the like. But central tendency is a measure, variance is a measure of how much things change from one observation to another. So we have variance, and it's measured, often represented by sigma squared. That's the Greek letter sigma, lowercase squared. Or especially when talking about estimates of the variance, we sometimes say S squared, or we say standard deviation squared. The variance, the standard deviation is the square root of the variance. Okay. So for population variance, the variance of some random variable x is defined as the summation I equals 1 to infinity of the probability that x equals x sub I times x sub I minus mu squared. All right, so mu sub x. That mu sub x is the mean, we just defined it, of x. That's the expectation of x, or also E of x. So it's the probability weighted average of the squared deviations from the mean. If it moves a lot either way from the mean, then this number squared is a big number. So the more x moves, the bigger the variance is. Okay. There's also another variance measure, which we use in the sample, or also var, sometimes used. So this is sigma squared. There's also another variance measure, which is for the sample. And when we have n observations, it's this, the summation I equals 1 to n of x minus x bar squared all over n. Oh, this should be squared. Okay, so that is the sample variance. Now, some people will divide by n minus 1. I suppose I would accept either answer. I'm just keeping it simple here. They divide by n minus 1 to make it an unbiased estimator of the population variance. But I'm just going to show it in a simple way here. So you see what it is. It's a measure of how much x deviates from the mean. But since it's squared, it weights big deviations a lot, because the square of a big number is really big. And so that's the variance. All right, so that completes central tendency and dispersion. We're going to be talking about these in finance as regards returns, because generally the idea here is that we want high returns. So we want a high expected value of returns. But we don't like variance. So expected value is good. Variance is bad, because that's risk. That's uncertainty. That's what this whole theory is about. How to get a lot of expected return without getting a lot of risk. Now, another concept that's very basic here is covariance. And covariance is a measure of how much two variables move together. Okay, so covariance is covariance. We'll call it. Now we have two random variables. So the covariance of x and y. I'll just talk about it in the sample terms. It's the summation I equals 1 to n of x minus x bar times y minus y bar all over n. Okay? So x, this is the deviation of, for the I subscript, meaning we have a separate I, x sub I and y sub I for each observation. So we're talking about an experiment when you generate, each experiment generates both an x and a y observation. And we want to know whether when x is high, y also tends to be high, or whether it's the other way around. If they tend to move together, if when x is high and y is high together at the same time, then the covariance will tend to be a positive number. Or also, if when x is low, y also tends to be low, then this will be a negative number, and so will this, so their product is positive. All right? So a positive covariance means that the two move together. A negative covariance means that they tend to move opposite each other. So if x is high relative to x sub I, this is positive, then y tends to be low relative to its mean, and this is negative. So the product would be negative. And if you get a lot of negative products, that makes the covariance negative. Okay. And then I want to move to correlation. So this is a measure It's a scaled covariance. The correlation, now we tend to use the Greek letter rho, or if you were to use Excel, it would be correl, or sometimes I say cor. That's the correlation, okay? This number always lies between -1 and +1. And what it is defined as rho is equal to the covariance of x and y divided by the standard deviation of x times the standard deviation of y. Okay? That's the correlation coefficient. So that has kind of almost entered the English language in the sense that you'll see it quoted occasionally in newspapers. So I don't know how used to it. Where would you see that? They would say there is a low correlation between SAT scores and grade point averages in college. Or maybe it's a high correlation. I don't know does anyone know what it is? But you could estimate a correlation. It's probably positive. I bet it's way below 1, right? But it has some correlation. So maybe it's 0.3, okay? That would mean that people who have high SAT scores tend to get higher grades. If it were negative, it's very unlikely that it's negative, right? It couldn't be negative. It couldn't be that people who have high SAT scores tend to do poorly in college. So that if you want to quantify how much they relate, then you have to look. You can look at the correlation. Okay. So I want to move to regression. And this is another concept that is very basic to statistics, but it has particular use in finance. So I'll give you a financial example. Okay. So the concept of regression goes back to the mathematician Gauss, who talked about fitting a line through a scatter of points. So let's draw, I took my watch off, I see my time here. Let's draw a line through a scatter of points here. So this is, I want to put down on this axis the return on the stock market. And on this axis, I want to put the return on one company. Let's say Microsoft, okay? And I'm going to have each observation as a year, okay? I shouldn't put down a name of a company because I can't reproduce this diagram for Microsoft. Let's not say Microsoft. Let's say Schiller Inc., right? There's no such company, so I can be completely hypothetical. Let's put 0 here, because and these are not gross returns, these are returns. So they're often negative, okay? And suppose that in a given year, and say this is -5, and this is +5, this is -5, and this is +5. Suppose that in the first year in our sample, the company, Schiller Inc., and the market both did 5%. So that puts a point right there, okay, at 5 and 5, okay? And in another year, however, the stock market lost 5%, and Schiller Inc. lost 7%. So we'd have a point, say, down here, right, at 5 and 7, all right? So this could be 1979. This could be 1980. And we keep adding points. So we've got a whole scatter of points, all right? It's probably upward sloping, right? Probably when the overall stock market does well, so does Schiller Inc., all right? So what Gauss did is said, let's fit a line through the point, the scatter of points. And that's called the regression line. And he chose the line so that, this is Gauss. He chose the line to minimize the sum of squared distances of the points from the line. So these distances are the lengths of these line segments. So to get the best fitting line, you find the line that minimizes the sum of squared distances. And that's called the regression line. And the intercept is called alpha. There's alpha. And the slope is called beta. Okay, so that's maybe a familiar enough concept to you. But in the context of finance, this is a major concept. The way I've written it, the beta of Schiller Corporation is the slope of this line. Okay, the alpha is just the intercept of this curve. We can also do this with excess returns. I will get to this later, where I have the return minus the interest rate on this axis, and the return minus the market return minus the interest rate on this axis. And in that case, alpha is a measure of how much Schiller Inc. Outperforms. We'll come back to this. But beta of a stock is a measure of how much it moves with the market. And the alpha of a stock is how much it sort of outperforms the market. We'll have to come back to that. These are basic concepts. Okay. So I wanted to, another concept, I guess I've been implicit in what I have, is there's a distribution called the normal distribution. And that is, I'm sure you've heard of this, right? If you have a distribution that looks like this, it's bell-shaped, right? This is x, and I have to make it look symmetric, which I may not be able to do that well. Okay, and this is f of x. The normal distribution is f of x is equal to the 1 over square root of 2 pi sigma e to the minus x minus mu squared over 2 sigma. It's a famous formula, which is due to Gauss again. We often assume in finance that random variables, such as returns, are normally distributed. So this is called the normal distribution, or the Gaussian distribution. It's a continuous distribution. I think you've heard of this, right? This is high school material. But I wanted to emphasize that there are also other bell-shaped curves. This is the most famous bell-shaped curve, but there are other ones with different mathematics. And of particular interest in finance are fat-tailed alternatives. So it could be that a random distribution, and I don't have colored chalk here, I don't think. No, so I will use a dashed line to represent the fat-tailed distribution. Suppose a distribution looks like this. Okay? And then I have to try to do that on the other side as symmetrically as I can. Okay? These are the tails of the distribution. This is the right tail, and this is the left tail. Okay? And you can see that the dash distribution I drew has more out in the tails. Okay? So we call it fat-tailed. This refers to random variables that have fat-tailed distributions are random variables that occasionally give you really big outcomes. So you have a chance of being way out here with a fat-tailed distribution. And it's a very important observation in finance that returns on a lot of speculative assets have fat-tailed distributions. That means that you can go through 20 years of a career on Wall Street, and all you've observed is observations in the central region. And so you feel you know pretty well how things behave. But then all of a sudden, there's something way out here. This would be great good luck if you're long. Now suddenly, you've just got a huge return that you just would not have thought was possible. You've never seen it before. But you can also have an incredibly bad return. And this complicates finance because it means that you never know. You never have enough experience to get through all these things. it's a big complication. My friend Nassim Taleb has just written a book about it called, maybe I'll talk about that, called The Black Swan. And it's about how so many plans in finance are messed up by rare events that suddenly appear that out of nowhere. He called it the black swan because if you look at swans, they're always white, right? You've never seen a black swan. And so you end up going through life assuming that there are no black swans. But in fact, there are. And you might finally see one. You don't want to predicate making complicated gambles under the assumption that they don't exist. So Taleb, who's a Wall Street professional, talks about these black swans as being the real story of finance. Now I wanted to move away from statistics and talk about present values, which is another concept in finance that is fundamental. And so let me, and then this will conclude today's lecture. What is a present value? This isn't really statistics anymore, but it's a concept that I wanted to include in this lecture. People in business often have claims on future money, not money today. For example, I may have someone who promises to pay me $1 in 1 year, or in 2 years, or 3 years, okay? The present value is what that's worth today, okay? So I may have a IOU from someone, or I may own a bond from someone that promises to pay me something in a year or 2 years. According to time-honored tradition in finance, if it says that it's a promise to pay $1, it's not worth $1 today. It must be worth less than $1. So what you could do hundreds of years ago and can still do today is to go to a bank and present this bond or IOU and say, what will you give me for it? Okay, and so the bank will discount it. Sometimes we say present discounted value. So the banker will say, well, you have $1 a year from now, but that's a year from now, so I won't give you $1 now. I'll give you the present discounted value for it. Okay? Now, I'm going to abstract from risk. Let's assume that we know that this thing is going to be paid, so it's a matter of simple time. All right? Of course, the banker isn't going to give you $1 for something that is paying $1 in a year, because the banker knows that $1 could be invested at the interest rate. And so let's say the interest rate is R. Okay. That would be a number which like 0.05, which is 5%, which is 5 divided by 100. Then the present value of $1, the present PDV or PV of $1 equals 1 all over 1 plus R dollars. Okay? That's because the banker is thinking, well, if I have this amount right now and I invest it for 1 year, what do I have? I have 1 plus R times 1 over 1 plus R. It's $1. So that works out exactly right. So you have to discount something that's one period in the future by dividing it by 1 plus R. This is present value of $1 in one time period, which I'm taking to be a year, but it doesn't have to be a year. The interest rate has units of time, so I have to specify a time period over which I'm measuring an interest rate. So typically it's a year. So if it's a 1 year interest rate, the time period is 1 year, the present value of $1 in one time period is given by this. The present value of $1 in n periods is 1 all over 1 plus r to the nth power. That is, that's the, all there is to this then. I want to talk about valuing streams of payments. Suppose someone has a contract that promises to pay an amount each period over a number of years. We have formulas for these present values, and these formulas are well known. I'm just going to go through them rather quickly here. Simplest thing is something called a console or perpetuity. A perpetuity is a asset or a contract that pays a fixed amount of money each time period forever. We call them consols because in the early 1700s, the British government issued what they called consols, or consolidated debt of the British crown, that paid a certain amount of pound sterling every, I think it was every 6 months, forever. And you may say, what audacity for the British government to promise to pay anything forever. Will they be around forever? Well, you know, as far as you're concerned, it's good enough as forever, right? Maybe someday the British United Kingdom something will happen to it. It will fall apart or change. But that is so distant in the future, we can disregard that. So we'll take that as forever. And anyway, the government might buy them back too. And so, you know, who cares if it isn't forever? Well, let's just talk about it as forever. So let's say this thing pays £1 a period forever, okay? What is the present value of that? Well, the first, each payment we'll call a coupon, okay? Okay, so it pays £1 1 year from now. Let's say it's 1 year, just to simplify things. It pays another £1 2 years from now. It pays another £1 3 years from now. The present value is equal to, remember, it starts 1 year from now under assumption. We could do it differently, but I'm assuming 1 year from now. So the present value is 1 over 1 plus r. It's £1 over 1 plus r for the first year, right? Plus, for the second year, it's £1 over 1 plus r squared. For the third year, it's £1 all over 1 plus r cubed. And that goes on forever. So that's an infinite series. And you know how to sum that, I think. Anyway, I'll tell you what it is. It's 1 over r. Or it'd be £1 over r. Generally, if it pays C dollars for every period, the present value is C over r. And so that's the formula for the present value of a console. All right, that's one of the most basic formulas in finance. The interesting thing is it means that the value of a console moves inversely to the interest rate. The British government issued those consols in the early 1700s, and while they were refinanced in the late 19th century, they're still there. And if you want to go out and buy one, you can get on your laptop right after this lecture and buy one of them. And you've got something that will pay you something forever. But you're going to know that the value of that in the market moves opposite interest rates. So if interest rates go down, the value goes up. If interest rates go up, the value of your investment goes down. Okay. Another formula is what if the console doesn't pay? Well, okay, what if, sorry. Next thing is a growing console. I'm calling it a growing console, even though the British consoles didn't grow. Let's say that the British government didn't say that they'll pay £1 per year, but it'll be £1 the first year, and then it'll grow at the rate g. and will eventually be infinitely large. All right? So you get 1 pound the first year. You get 1 plus g pounds the second year, etc. 1 plus g squared the third year, and so on. The present value of this, suppose it pays, let's say it pays c pounds each year. So it would be c times this. All right? It would be c times 1 plus g cubed in the third year, etc. Then the present value is equal to c all over r minus g. That's the formula for the value of a growing console. G has to be less than r for this to make sense. Because if it's growing faster than the rate of interest, this infinite series will not converge, and the value would be infinite. And you might ask, well, then how does that make sense? What if the British government promised to pay 10% more each year? What would the market value that at? The formula doesn't have a number. Well, I'll tell you why it doesn't have a number. The British government will never promise to pay you 10% more each year because they can't do it. And the market wouldn't believe them because you can't grow every year faster than the interest rate. And that's one of the most basic lessons. You can't do it. OK. One more thing, I think, which would be relevant to the there's also the annuity formula. And this is a formula that applies to what if an asset pays a fixed amount every period and then stops? That's called an annuity. OK? So an annuity it pays C, I'll go back to dollars, C dollars, starting in t equals 1, 2, 3, and n is the last period, and then it stops. A good example of an annuity is a mortgage on a house. When you buy a house, you borrow the money, and you pay it back in fixed, it would usually be monthly, but let's say annual payments. All right? You pay every year a fixed amount on your house to the mortgage originator. And then after so many, n is 30 years typically, you would then have paid off. It used to be that mortgages had called a balloon payment at the end, which means that you'd have to pay extra money at the end. But they decided that people have trouble doing that. It's much better to pay a fixed payment and then you're done. Otherwise, if you ask them to pay more at the end, a lot of people they won't have the money. So we now have annuity mortgages. What is the present value of an annuity? Okay, and so that is the present value of an annuity is equal to the amount, what did I say, is C times 1 minus 1 all over 1 plus R to the nth power all over R. And so that is the present value of an annuity. I wanted to say one more thing because I realize that you have to, your first problem set will cover this, is to talk about a concept that applies probability theory to economics, and that is expected utility theory. And then I'll conclude with this. In economics, it is assumed that people have a utility function which represents how happy they are with an outcome. Okay? And so we typically take that as U. So if I have a monetary outcome, I have a certain amount of money, X dollars, how happy I am with X dollars is called U of X. Okay? And this, I think, you've gotten from other economics courses. We have something called diminishing marginal utility. Okay, and the idea is that for any amount of money, if this x is the amount of money that I receive, utility as the function of the amount of money I receive is downwardly concave. The exact shape of the curve is subject to discussion, but the point of diminishing marginal utility is that as you get more and more money, the increment in utility for each extra dollar diminishes. Usually we say it never goes down. We don't have it going down. Cross that out. That would be where having more money makes you less happy. That may actually work that way, but our theory says no. You always want more. But it's always upward sloping, but it may be after a while you get close to satiation where you've got enough. All right, and so the theory, I mentioned this last time. I was philosophizing about wealth. And I said, what are you going to do with $1 billion? We have many billionaires in this country. And I think that the only thing you have to do with it is philanthropy. They have to give it away because you are essentially satiated. Because you can, as I said, you can only drive one car at a time. And if you've got 10 of them in the garage, it doesn't really do you much good because you can't do it. You can't enjoy all 10 of them. So it's important. That's one reason why we want policies that encourage equality of incomes. Not necessarily equality, but reasonable equality, because the people with very low wealth have a very high marginal utility of income. And people with very high wealth have very little. So if you take from the rich and give to the poor, you make people happier. But we're not going to do that in a Robin Hood way, but in finance we're going to do that in a systematic way through risk management. So we're going to be taking away from lucky people. You know, you think of yourself as randomly on any point of this. You don't want, you know that you'd like to take money away from yourself in the high outcome years and give it to yourself in the low income years. So what finance theory is based on, and much of economics, is based on the idea that people want to maximize the expected utility of their wealth. Okay, and so since this is a concave function, it's not just the expected value. To calculate the expected utility of your wealth, you might also have to look at the expected return, or the geometric expected return, or the standard deviation, or you might have to look at the there's so many different aspects that we can get into. And so this underlying theory motivates a lot of what we do, but it's not a complete theory until we specify the utility function. Of course, we will also be talking about behavioral finance in this course, and we'll at times be saying that the utility function isn't the idea that people are actually maximizing expected utility may not be entirely accurate. But in terms of the basic theory, that's the core concept. And I have one question on the problem set that asks you to think about how you would handle a decision whether to gamble based on based on expected utility theory. That's a little bit of a tricky question, so do the best you can on it, and try to think about what this kind of theory would imply for gambling behavior. All right, so I will see you on Friday. That's 2 days from now in this room.